My name is Scott Perello. I'm the COO and a partner with the Building Envelope Group. Thanks for joining me today. Today we're going to talk about building envelope basics, more specifically an introductory overview to building envelopes, what exactly that means, the different functions, different types, how water and moisture and air and whatnot is handled in various building envelope systems, and how we assess issues when encountered, whether it be water intrusion or cracking or other issues that we get called in to address. So anyway, let's dive in. What is a building envelope? The actual definition is the physical separator between the conditioned and unconditioned environment of a building, including the resistance to air, water, heat, light, and noise transfer. Fantastic. But what does that really mean in simple terms? In simple terms, the external skin or enclosure of the building that helps to control the interior environment by keeping the exterior environment out, from the roof to the foundation. Building envelope, building enclosure, these are synonymous terms you'll hear in the industry often. So the three primary functions of a building envelope: structural support, environmental and climate control, and the finish or aesthetics. Structural support: the building envelope elements, foundation, walls, framing elements, the roof system, provide primary and or secondary structural functions, either by directly, such as in the foundation, or indirectly, exterior walls that are tied to concrete or steel columns or floor slab edges on the interior. They're carrying loads or protecting interior structural elements, such as a curtain wall, glazing system, protecting structural steel and concrete behind the face. Note, older buildings, often early 20th century and before, typically utilize very thick mass masonry exterior walls that were the primary structural load-bearing walls, unlike more modern buildings where the primary loads are typically carried inboard of the facade. I'll touch on mass masonry walls shortly. Environmental climate control. The building envelope, when properly designed and maintained, provides protection from the exterior elements, rain, wind, UV rays, so forth, while maintaining the interior climate controls, heat, AC, humidity, and separation from the exterior environment through all seasons and weather conditions. Note, if water and other elements are not properly controlled through the entire building envelope, structural elements are subject to potential corrosion and ultimately failure, leading to serious structural deficiencies and complete collapse. As an example, many of you may remember the devastating collapse that happened in Florida a few years back. I'm familiar with the consulting engineer that was involved in that, and it was a very unfortunate results that could have been prevented from the lack of deferred maintenance, and that's basically, we see that all too often in the industry, where deferred maintenance is actually not just keeping water out from a nuisance standpoint. It's keeping water out, or deferred maintenance is allowing water in and it's affecting the structural integrity of the building. Hits steel components, which are subject to corrosion from water intrusion, which can lead to cracking of concrete elements. So deferred maintenance is not good. Not just, as I said before, for saving money, it's a life safety issue. The finish and aesthetics. A building envelope or skin is the first thing people see on a building. Although the building envelope and its facade, which is the face of the building, they can be very utilitarian and boring from a design standpoint, because they'll still be doing what it's intended to do primarily, which is the function of protecting the interior from the exterior. But the form following the function that would satisfy that. But most people want to work and live and play in a building that's a little bit more interesting to look at. So this is why the building facades can be in so many different building materials, colors, shapes, so on and so forth. On a side note, I used to be a landmarks commissioner myself, and historic preservation goals are really not just to protect the pretty buildings, the famous cathedrals and landmarks that we all know. And those are very important. But also the utilitarian facades, some of them, they tell the story, the architectural history of our country, of our communities. And so saving those as well, also is important for historic preservation goals. All right. So there's three primary types of building envelopes, or facades, I should say. There's other subsets of these three, but the three primary ones are mass masonry walls, transitional walls, cavity and curtain walls. Mass masonry. This is the type of construction that's been used basically from the beginning of human building history. As I touched on before, exterior, bearing walls, thick, solid masonry, stone and brick and other components, without the use of steel or anything on that order. And they could only go so high. That's the thing. But basically the whole concept of, say, the pyramids, thicker at the bottom, a little thinner at the top. But basically, the higher you go, the more susceptible it could be to collapse if they're not brought inward. So that hence the design of a pyramid, or the fact that on a mass masonry wall, they get a little bit thinner the higher they go. Here's some examples of mass masonry walls. These photos I took myself. The one on the left is actually from my hometown of Waltham, Massachusetts. It is the Boston Manufacturing Company, and mass masonry walls. I'm a bit of a history nerd, so I guess it kind of goes with the territory of what I do. But that's where the Industrial Revolution in America started, and where raw materials were turned into a finished product all under one roof. And that kind of spawned the, not just, the need to create more textile mills, but also the same kind of construction. So just a little further up the road along the Merrimack River in Massachusetts, you have Lowell and Lawrence and places like that where they built dozens of these kind of structures for that purpose. The middle building is actually a ruined castle. A number of years ago, I hiked along Hadrian's Wall, a 2,000-year-old stone wall up in northern England. And this just came across this castle ruin, and you can see the thick mass masonry walls that are still standing. And the one on the right is just a typical cross section of a wall where you can see, several weiss thick. That's about a 2-foot thick wall. You can see a solid stone on top of that. That's pretty typical of mass masonry wall construction. Transitional walls. So where mass masonry walls did not typically incorporate concrete and steel elements because they weren't really even available yet, during the early 20th century, in order to transition into building taller buildings, concrete and steel were now incorporated into the structural design. The exterior walls were still typically bearing walls, but the primary loads were now carried by interior columns made of concrete and steel and beams made of concrete and steel. The exterior walls usually incorporated masonry and steel elements into solid walls, and eventually concrete masonry units were used with brick to build composite walls. Composite is just basically where you have two different types of materials or more working together for the same function. So they all share the same load through them, and they share the same function as far as how they manage moisture and whatnot. These walls were often thinner, but much more vulnerable to water intrusion and structural corrosion than the older mass masonry walls, and eventually the cavity and curtain wall systems used primarily today. So here's some examples of transitional walls. University building out in the western U.S. You can see the terracotta cornice and the steel elements incorporated into its design and construction. And you can see how vulnerable it is. The reason we were called out there in the first place is you can see these pieces. These are dental pieces. If this was a mass masonry wall, which you can see in a lot of older construction, even in U.S. cities, these would be cantilevered solid stones. And you can see them in big cities like my hometown of Boston and in Philadelphia and other cities around. You will see older buildings that are mass masonry walls that have similar cornices of solid stone. But in this case, the transitional buildings use lightweight terracotta, which is clay, fired similar to brick. And now they're incorporating steel and other components into that. But basically, as I said, we got called up because one of these dentil pieces, 2 of them actually fell to the ground. And luckily nobody was injured. But you can see how they're basically hanging here. So you have an interior steel construction, which these shelf angles are bolted to interior superstructure made out of steel. And they're hanging from basically 9-gauge wire to these rebar, where these dentils are sitting inside of that. But you can see it's pretty precarious. Once water gets in there, it starts to corrode the steel. The steel starts to expand, puts tension on that. You can see the cracks right here, pretty severe. And then that just basically, it's a deck of cards from there. So these are very vulnerable. The picture on the right is a quasi-modern multi-family apartment condominium building I was involved with in Washington, D.C. And you can see basically this is a common bond masonry wall where basically every 7th or 8th or 6th courses of brick are tied into the backup wall. This is pretty common. It's called common bond or American bond as far as the brick pattern. But what's happening here is you have concrete masonry units as the backup wall. This is near the top of the roof, so that's poured concrete. But basically the exterior brick is tied into the CMU. And although it looks like a gap there, these are solid. Furthermore, so if water gets in, it doesn't really have any way to get back out. So it just sits in pores and cavities and goes whichever way via gravity and air pressure. It moves through the wall. You can see this. This is a loose laid, basically sitting in their lintel, steel lintel above a window opening, where the brick is holding the weight of the brick above that. This is actually a hole. I could actually put my whole hand through here. So very bad condition. No way that the water is managed there, and it's thin. It's not like the mass masonry walls where you have several widths of brick, which water can move in and out. Here you have steel, which is very vulnerable to corrosion. Cavity and curtain walls. They're the most widespread construction used today, especially in commercial buildings. Cavity wall systems use multiple materials for the facade, such as brick masonry, but also they are attached to the backup wall. They typically have a space between that allows air and moisture to move via gravity and air pressure. Curtain walls are typically non-structural walls hanging from structural components directly behind and are typically constructed of glass or metal panels, mixture of both with aluminum framing. These large glazing systems rely on sealants, gaskets, and the aluminum frame weep hole systems to manage water and air penetration at the exterior side. I will dive more into cavity walls here shortly because that's the most typical construction that we encounter, especially when dealing with complicated leak mitigation issues. So on the left is just a typical cross-section of a cavity wall system, and they're all different. Sometimes you'll see this rigid styrofoam insulation in the cavity itself, such as this. Sometimes you don't see it at all. Sometimes they rely just on that. Sometimes the sheathing here is the only thing you see. And then the flashing, you can see that's the throughout flashing there. You can see these are weeps. These are called cell vent weeps. There's different ways that weeps are made. Sometimes they're tubes, plastic tubes. Sometimes they're actually cotton rope that allow moisture to wick out. There's a lot of ways but basically the long and short of it is moisture, water comes down via gravity and other forces and it exits out there. That's your typical cavity wall. You can see the space, typically anywhere between 1 inch and 2 inches is pretty typical in the design here. And on the right, you can see it's a typical curtain wall. So behind there's a superstructure that all of this glass and aluminum is bolted to. Sometimes the glass panels themselves are connected together with structural sealants. Sometimes they're with a combination of structural sealants and clips. Sometimes they're all mechanically attached and just using weatherproof joint sealants. So they're all a little bit different, but they all have pretty much the same concept where they're non-load bearing and they're basically just hanging from the superstructure behind. So when it comes to addressing water issues, there's really two things that must be understood in order to assess the how water is moving through the wall or designed to move through the wall, and how you would mitigate it and and design a repair that makes sense. So you have two types of systems: you have barrier walls and drainage plane walls. It's very important that we try to understand which it is when we design or repair. Barrier walls. Generally speaking, the majority of mass masonry walls and transitional walls are solid. Therefore, are designed to manage water at the surface. That's really important to understand. Whether they're the transitional walls, thinner, only maybe, one width of brick and one width of CMU, or they're fat, mass masonry walls with several widths of brick. The intent is still that you want to prevent water coming in the first place at the outside skin. And that's sometimes easier said than done over time. This generally means if water and air are allowed to enter the wall system through a crack or a hole in brick, mortar, whatever it might be, and allowed to pass through the system, then there's no additional protection. There's no secondary line of defense behind that. Once it gets through that brick or stone, whatever it might be, it's going into the interior of the building. Large mass masonry walls typically manage it better. As I said before, they're thicker, they can absorb the moisture and move, but the concept is still the same. By design, they're all barriers because you have to basically have a barrier at the face of the building. Drainage plane walls. Cavity walls are the primary construction used over the past few decades. And except for curtain wall systems, which are modern, but they are more barriers as well, these are designed to allow potential air and moisture intrusion from the exterior face, but are designed to manage these conditions by the weather-resistant barrier, the WRB, within the exterior wall system behind the face. WRB systems designed and installed over the past few decades range considerably in the types of materials and functions, but essentially are designed to manage air, liquid water, water vapor within the wall system and provide a path to the exterior, preventing water intrusion and controlling the interior climate. Generally speaking, WRBs are a combination of metal and or rubber flashings located at window heads, steel lintels, and penetrations, miscellaneous other fenestrations, which are windows, doors, louvers, any kind of opening, and sheet materials, whether it's polyethylene sheet wrap, say Tyvek or building wrap, asphalt building paper. This was very common for decades. Pre-cured neoprene, very common for flashing, especially in commercial buildings. You would often see a combination of asphalt building paper, stapled to the face of the backup wall or attached somehow, and then especially in wood frame or that kind of thing, and where neoprene flashings were put right at the floor lines or at window openings. Liquid applied systems, more modern, are also used, and especially for air barriers, and I'll touch on air barriers soon. Once again, what they have in common is they're all attached to the sheathing, or whether it be insulation sheathing. There's a lot of different scenarios how they do that, but ultimately the purpose is that it's a secondary line of defense. That's what the WRB is. It's supposed to be a continuous, basically weather-resistant barrier behind the skin of the building. It's not a matter of if water will get through the exterior skin. It's just a matter of when. So although preventing liquid water from entering behind the WRB is important, allowing water vapor to escape can also be a key factor in choosing a WRB. Considerations are climate, code requirements, building occupancy, material composition. There's a lot of factors that go into what WRB is used. So, here's just some examples. Most everyone is seeing Tyvek on the side of house construction or similar. There's a lot of different types of house wraps like that. This is your typical asphalt building paper. pretty common for many years. Here's some rubber materials. With this one, once again, they have polystyrene insulation on top of that, and this is called mortar net. So basically, when they're laying brick masonry walls, as the bricklayer is installing or laying the brick, sometimes what happens is the excess mortar can extrude beyond or out of the backside and fall down into the cavity and clog that. So obviously quality controls are in place to prevent that from happening, but it does happen. So what happens is in design, you just assume that someone's going to fall down there. So you put this mortar net at the bottom. It basically allows moisture to get around any mortar droppings and still find its way down through the holes in this mortar net and work its way eventually to the weep holes, as you can see right there. All right, so through wall flashing. So this is something that we deal with a lot in remediation work. Once we get a call for water intrusion, if it's a modern building, typically built after the 1980s, office buildings, multifamily, whatever it might be. Typically, it was designed with a cavity, and we go out there, we perform water testing, and we see it's leaking above window heads and things along that order. And so we usually assume that there is a lack of adequate flashings or WRB/flashing assemblies above that. Or they're just inadequate, or they were improperly installed, or they don't have end dams. And I'll touch a little bit on end dams. So through all flashing, or through all, with the both spellings are acceptable. Flashing systems are designed to be an integral part of a complete and continuous WRB system. When installed as a remedial repair for water intrusion, typically due to a lack of or inadequate flashings or end dams above the windows and doors, the process typically involves temporarily removing the veneer, whether it's brick or precast, whatever it might be, preparing the backup sheathing. Once again, you saw in the last slide, sometimes they have insulation on top of that. You'd have to remove that insulation and to install the through-wall flashing. More times than not, though, I don't see it that way. I usually see the insulation inboard of the sheathing. So you prepare that material for installation of typically a pre-cured rubber and metal flashing combination that will sit right down upon the steel lintel. And then it's attached mechanically to the backup wall, has a termination bar with sealant on the top. So if any liquid water is running down above that, it hits that, it runs on top of it, and it exits the wall system via weep holes or cell vents. And installing proper end dams to prevent the water from moving laterally. Obviously, I've touched on installing weep tubes or cell vents and mortar net. And then basically ensuring the existing WRB material properly laps over the new flashing system. If there is a WRB, such as Tyvek or building wrap or asphalt paper, whatever it might be. And then obviously reinstalling the veneer material. So in this case, here's just a couple of examples, where the brick was removed, and you can see the flashing system that they put in. These are the end dams. So basically what happens is if water, I see a lot of situations where we remove brick or whatever it might be, and we see a flashing in there, but it doesn't have end dams. So what'll happen is the water gets down and it moves laterally this way. It'll get in the building just at the end, unless it's continuous all the way around, which isn't often the case. It will get into the building that way. So end dams run perpendicular to the face of the building, and basically, like they sound, they dam up the water and then force it to come back out through weep holes as well. As I said before, here's the termination bar at the top, which mechanically attaches it to the backup wall. You can see the sealant there. So any moisture that kind of comes down here would hit that and work its way out. And here's the aforementioned mortar net. So and you can see here they're reinstalling the brick masonry. There's the flashing system. They brought the WRB over on top of it. They have some wall ties here for installing the brick. All right, so air barriers. We hear this a lot nowadays, pretty modern. There are basically two primary forces upon moisture. And I used to do a lot of forensic studies years ago where we would really get down into the weeds in test chambers and figuring out how water, liquid water and water vapor move through a wall system. And there's a lot of forces going on there. You have, vapor drive, you have gravity, and you also have negative air pressure. And air pressure, differential between the outside and the inside. You have a temperature differential between the outside and the inside, and air, differential, as well as within the air cavity itself. So what we have found over the years is that from a lot of study, that really the larger force on liquid water is instead of just gravity is actually negative air. So, that allows moisture to wick inside from negative air. It's drawing that liquid water into the building from, air pressure. Most of us can relate, say in our homes, when your air conditioning system kicks on, often you'll see a door that was just barely open, closed shut, and that's not a ghost. That's negative air pressure. So it's quite capable of drawing water in that is trying to exit the building. So what they came up with is say, okay, well, instead of just, building wall systems that allow gravity to have the water come down, let's make, pretty much a bulletproof WRB. That is continuous. Now, obviously, the intent of any WRB should be continuous, but it doesn't always work out that way, and they're lapped. So sometimes it's not 100% sealed, especially in the areas that aren't covered by rubber flashings and metal flashings. So what they do is basically create a vacuum by a continuous yet moisture vapor permeable. So it allows these air barrier systems allow moisture vapor from the inside to be drawn forward to the exterior, which is very important. Otherwise, you'd have moisture issues just from moisture vapor being trapped. So they're very permeable, but at the same time, they don't let liquid water come inboard. And they create basically a vacuum so that the only force upon them really is the gravity and the exterior draw of air. So years ago, it was Wisconsin and Massachusetts were the first states to actually codify the use of air barriers in commercial construction. And now many states have followed suit since. So it's pretty much the new norm on building construction facades. And these are just typical systems. You have sprayed on systems, you have some panel systems, which uses tape and other and sealants for any penetrations through them. It's a complicated process in the building construction nowadays, though. You have multiple subcontractor trades building these things where you have the bricklayers working with the team that's putting on the weather resistive barrier or air barrier. And the chances of doing an entire facade without any holes or any defects is very difficult to pull off. So, even with the new stringent codes and even with the increased construction supervision, which I see more these days than I did 20, 30 years ago, you're still going to have defects in these systems. So something to keep in mind, when getting called out for a leak and you see, it's an air barrier, well, chances are there might be a defect in the system as well. So to wrap things up, just rhetorical questions here to consider when performing a leak investigation regarding water intrusion. Is the wall system a barrier or drainage plane? Take a look at it. Try to understand its vintage. If there's as-built drawings, you can always take a look at those and see what the intent is. But typically you can tell by the vintage. A telltale sign on a brick facade. If you see running bond masonry in a modern building, typically it's got some sort of air barrier behind that. A cavity behind that. And then if you see common bond, where you see header courses every 7 or 8 courses, it's often a telltale sign that it's a solid or composite wall, because those header brick are turned perpendicular, and basically would prevent water from moving through a cavity because they're blocking the cavity. So that's usually a telltale sign of a composite wall that's solid. How can I tell if it's a barrier drainage plane if it's not obvious? Well, as I just mentioned, you might look at as-built drawings, things along that order. You may have to do destructive testing and open the thing up and see what you see as typical. Is it ever appropriate to install a WRB and or through-wall flashing in a mass masonry or transitional composite solid wall? At times, yeah. And I mentioned what are fake headers. So, I see this more often than I used to. I know my times in the Washington, D.C. market, I've encountered a number of buildings where they have false headers or fake headers, where basically they're during construction, they're actually not extending back to the backup wall. And there actually is a cavity that's being honored or it's in place. So that allows moisture to get back through there. So sometimes the best way to really perform an investigation is to, go through the typical steps of water testing and designing a repair, but always assume that, if you're going to do a full-on global replacement repair or through-wall flashing repair, open up the wall, look at the as-built conditions in 2 or 3 locations, and then if you have to switch the design based on what you actually encounter, then that's okay before you get too deep into the project. If a topical repair, such as joint replacement, repointing, or water repellent application seems to mitigate a leak, should you consider the job done? Well, to me, it's like putting a Band-Aid on something. It might stop the bleeding, but do we know if there's an infection beneath the surface? After a cut. Sometimes the Band-Aid, that might stop the bleeding, but you should probably get in there and clean that thing out maybe at a later time if you can. So that's kind of the same logic. It might stop it temporarily, but if we know it's a cavity system, a topical repair isn't really addressing the root issue. Most likely it will find its way in there again from another entry point. Should you water test every time if obvious holes are not visually apparent at the assumed entry points? Well, I'm a big proponent of water testing. Open up the interior, especially if there's history of observed water intrusion at specific locations. Open those areas up for observation. Perform very specific water testing procedures so that you can monitor it and try to understand where the water is moving. Sometimes you isolate different components. I do another training module on water testing itself. Feel free to check that out and get a little bit deeper into that. Can you ever completely guarantee a waterproof building assembly? I saw a contract a few years ago where they literally, as a contractor at the time, they wanted me to sign off saying that we completely guarantee 100% waterproof building envelope. And that's pretty tough to do. It's a complicated thing. There's a lot of components and interfaces. It's not that simple. You can attempt, through barriers as well as WRB systems, which are complete and thorough, to waterproof the envelope as much as possible. But it's amazing over time through thermal expansion and contraction, volumetric expansion and contraction of various building components, and then you mix all these different building components together. Even if you do it right the first time, over time, issues are going to develop just from the life cycle of a building facade. So I'm putting together another training series on building envelope a little bit more in depth, and I find this particular book a good general overview. Michael Kubal, he's written several books, and I have a number of his books, and it's a good overall entry into waterproofing. So it's called the Construction Waterproofing Handbook. And it's a really good resource. So I recommend that. You can see the link down there. As I said before, I'm putting together a training series more in depth. We're going to study chapter by chapter on this particular book. So look forward to that. So once again, I appreciate your time. My name is Scott, BEG, and you can see my email and my phone there. Feel free to give me a shout and say hello, and shoot any questions you have to me via email, and I'll be happy to get back as soon as I can. Thanks, and have a great day.